Well, it's evening already. You're tired. Хорошо. So, my talk is, my lecture is a survey lecture, and it's about some class of special functions called elliptic hypergeometric integrals. It's a rather new class of transcendental special functions of hypergeometric type, which were discovered in this laboratory, room 218, and I will pinpoint which particular result which was obtained in that room. And the connection with the topic of this school is the fact that this story happened around 2000, and in 2008 it was found that this class of special functions describes superconformal indices of four-dimensional superconformal field theories, or simply four-dimensional supersymmetric field theories. And that breakthrough obtained by physicists essentially completely changed my point of view on the things which I have discovered, and that's what is the reason of my appearance here. So my talk will be mostly mathematical, but I will say a few words where in physics these guys emerge. So what are these integrals? Are integrals, that's clear. So I'm talking about contour integrals. No pointer, only this one. Okay, I see, you can see it. It's okay. So I will start immediately from the definition, which appeared 3 years after these first examples of such integrals have been found, and the definition is very simple. You take contour integral over some unspecified contour, usually it's some cycle, of some meromorphic function of variable u, complex variable, and you demand that this meromorphic function is a solution of the first order finite difference equation. Here's the equation, first order, with some coefficient f, which you demand to be an elliptic function, general elliptic function. So it means that this is a meromorphic function with some constants omega 2, omega 3, which are periods of this function. So doubly periodic meromorphic function is by definition is an elliptic function. You take it as a coefficient of the first order equation with the third constant omega 1 working as a shift in your finite difference equation. That's it. You solve this equation, substitute here, and you get by definition the elliptic hypergeometric integral. Well, now we have to solve this equation in order to see it explicitly what it is. First, I would like to pass.
The omega 1 and omega 2, 3 are different. I mean, the omega 2, 3 have the elliptic function, but delta only has the periodicity.
Yes, they look different. You see, these two constants emerge as periods, and this is just a third arbitrary. And I assume that all three of them are incommensurate, which means that they are not linear sums of these constants with integer coefficients is not zero. That's the meaning of the incommensurability. From these additive notations, I would like to pass to the multiplicative notations. For that, I introduce what is called basis, exponentials of the ratios of these constants. So you see, omega 2 is in the denominator of these things, and omega 1 and omega 3 is here. Q is this guy, and P is this guy. So these are the bases. And I introduce instead of u variable exponential of u divided by omega 2. And you immediately see that the periodicity of this type is already guaranteed as soon as I work with the functions of z, because this is a periodic function of this guy. Now I demand, I reduce my problem a little bit, I demand that this function is meromorphic not in u, but in this z variable. So I change notation. Instead of delta, I use rho and say that it depends now not on u, but on this combination of u. And so I take this as a kernel of my integral. Because of this change of variables, I have now a measure on the torus and this function as a kernel. So it's just slight reduction, but it is important constriction because meromorphic functions in z, they are definitely, of course, meromorphic functions in u, but not vice versa. Meromorphic functions in u are not obliged to be meromorphic functions of z. Logarithm is involved. So it's a substantial restriction. But it's more easy to understand what's going on in this case. So now I call this integral as an elliptic hypergeometric integral if this kernel satisfies this linear Q difference equation now. This is a complete analogy of this because in terms of this variable, shift by omega 1 is nothing else but as multiplication of z by q. So you multiply by q and pick up this H function, which is, again, as I said, just change of notation for the elliptic function. And ellipticity means that this function of variable z is invariant with respect to the multiplication of z by p. So in multiplicative notations, this is the definition of elliptic function. It must be p periodic, where p is multiplicative period. And you take it as a coefficient, and the first order Q difference equation, solve it, substitute here, and you get by definition, the integral. Here it's written, exponential 2 pi I u over omega 2 is z. So it's already a periodic in omega 2. Now, what I need a definition of infinite product of this type. So you take geometric progression with p modules less than 1, to form this product. It's very well defined, and so very useful, and it's the whole class of so-called Q special function is built basically from such type of infinite products. In this case, Q is replaced by P. Now, you saw already Jacobi theta function. I will need a piece of that, namely double infinite products, two infinite products. I will call this is a Jacobi theta function. I will use only that one. And it is related to the theta series, standard theta series. In this, through this, what is called the Jacobi triple product. Why it's triple product? Because this theta series equals 1, 2, and if you take it here, 3 infinite products. So I need only this piece, and that's a short theta function. And it has very nice important symmetries. So this is an exercise, easy exercise. Whenever you see this word exercise, it means that students should do it on their own to have fun and be very happy to see how it works. And it's quite pleasant. So multiply by p, it's the same as inversion of z, and it's minus the inverse of theta. So it's quasi-periodicity and inversion relation for theta functions. Now, there exists famous and very powerful theorem by Abel and Jacobi, which says that any elliptic function, h of z, which I have started from, can be written as the ratio of products of theta functions. So you see, tk and wk are some arbitrary complex variables. They enter as basically divisor points of this function, and you have to have this constraint. And then any such combination for any integer m is called order of elliptic function. So any elliptic function can be written in this form. It's a theorem. And it's very nice because you see from the words that something double periodic, meromorphic, and so on and so forth, you have explicit formula for this function in terms of theta functions. You immediately can work with that in a very constructive way. Okay, how to prove this theorem? It's rather easy. First periodicity is already there. Second periodicity, you take this ratio then you use these properties that multiplication gives you these constants, which means that you pick up from this ratio this product and from this ratio this product. And because of this constraint, it's 1. That's it. You prove the theorem. And you can prove inverse. You suppose that you have some elliptic function which divides the points given by some constants tk, wk. Then you immediately prove that it must have this form because you divide one function by another function, and it will not have zeros or poles in the parallelogram of periods, which means that this function is constant. And you prove that any function has such type form up to multiplication by a constant. So very powerful and nice theorem by basically Jacobi, because you use Jacobi theta functions. What for I need it? Because I have factorized the coefficient of my Q difference equation. And so it means that actually I have to solve a much simpler equation, namely this one. You take some function, multiply its argument by q, and you pick up this theta function, short theta function, as the coefficient. So as soon as you are able to solve this equation, you can solve immediately the original one because it's just the factorized object. And here comes the partial answer, because this is I'm giving you immediately the explicit expression for a particular solution of this equation. Here it is. So it depends now on two variables, p and q. Q emerges as the shift of the argument, and p emerges as the moduli parameter of the elliptic curve behind this business. So it's actually the moduli parameter of the theta function. And here is explicit form of the particular solution. And then exercises to find this solution for students from scratch. So you saw it once, now forget it. Now plug in here the factorized form of theta, one infinite product times another infinite product, and then piecewise solve again it by factorized form. For the first factor, this this denominator, the infinite product, give you the first factor, and this will give you the second factor. And you immediately will have a lot of fun and nice, pleasant feeling after you will be able to solve such a first-lookingly complicated equation. But it is very simple. And this function, it has a long, long story. And it starts on the generalized theory of gamma functions by Barnes. Then Jackson gave some particular example of this function, and emerged in Baxter's 80-vertex model implicitly. Explicitly, in the modern time, it was introduced by Rusinars, who gave actually the name to this function. Then some modular transformation properties of Feldman-Manchnik. And I was able to find another partner of this function. There is one more elliptic gamma function which works with the different type of values of the basic parameters. You see here you have to have both basic parameters modulus less than 1 for convergence of this infinite product. And you can actually find the solution of that original equation in the case when, say, Q is modulus equal to 1. So it's a different set of domain of values. But I will use only this elliptic gamma function. So you have the solution of this theta function equation, the Q difference with theta function coefficient, and immediately you find that del rho function, the kernel, is the product of the ratio of the products of elliptic gamma functions with the arguments of Vedian type, and this is the constraint you have to have for ellipticity. And that's it. You already reached the top level of special functions of hypergeometric type. You see it just in 2 slides, just knowing where to look at. And this integral involves all known hypergeometric functions of one variable, what's called univariate. And moreover, Q hypergeometric functions as well there. It corresponds to the case when P goes to 0 in this formula. And Q hypergeometric functions, it's also, it's already almost 30 years in the air. But it is actually a very old class of special functions introduced by Euler and many other mathematicians. And so Q hypergeometric equation was introduced shortly after Gauss. So it's also quite old special function class. But the elliptic, this class, emerged only 20 years ago. So basically, I introduced the first example of this type of integrals only in the year 2000, as I said, in this laboratory. But it comprises all. So in this sense, this is a really new class of special functions. Okay, let's go further. What? Integrate over Z. It is not fixed here, but in all cases which are interesting, it's a unit circle of positive direction. So it's a torus measure, and you integrate over circle which surrounds particular type of poles. So it's unit circle. You pick up some poles, some residues. You get integral plus some residue. That's all. So it depends on the choice of the contour, but the general definition is here. And now you have to work with this definition, what it can give you. So in this case, in the case of the torus measure, it's usually a unit circle of a positive direction. So as the best example which emerges in this case. Okay, a few properties of this elliptic gamma function. First of all, you see it's symmetric. This double infinite product was symmetric in QP. But the original equation you started from was completely unsymmetric in this Q and P. And this is a very unexpected property, that you start from equation with 2 parameters which enter non-symmetrical, but the solution is symmetric. And this is an enhancement of the symmetry, which you heard a lot about in Kim's talk today in the morning. So it means also that instead of the one equation, you have actually 2 Q equations. Q difference equation first, or the Q P difference equation with theta function is the modular parameter P, and theta function is modular parameter Q. And that means that actually you work with the objects living not on one, but on the product of elliptic curves. And the modular group SL2Z, which is associated with the elliptic curve, will be replaced in this case with modular group SL3Z. It's much more involved, and actually the modularity properties are not yet completely understood. It's one of the questions about these objects, how they live with these modularity properties. Here is the inversion relation. You flip your argument, and you get the inversion of the whole function. Then goes the quadratic transformation, and all these plus minuses mean that you actually have products of elliptic gamma functions. And so you just look the definitions and you understand what does it mean, this actually the product of 8 elliptic gamma functions. An important relation is this one, limiting relation. So it has the pole at z equal 1, so you cancel this pole and you get this double infinite product. This is important for computing the residues of the integrals which you are starting from. If you compute few residues, it's okay. It's a sum of elliptic functions, the residues. But if you try to shrink the contour of integration to 0, you get infinite number of terms, infinite series, and they do not converge. So these functions cannot be defined as infinite sums. But there are some special limits when you pick up a number of residues and kill the rest of the integral. And then you will get this finite term sum of elliptic functions. So that's how emerge this series. Terminating hypergeometric series emerge as the terminating sum of residues of particular sets of pole of these functions. But the functions themselves as functions, analytical functions, they're defined only as integrals. That's why I always stress that these are integrals, not just some. They are defined in the generic case as the integral. And here is the example which was the very first one where the whole story started in 2000. It's called elliptic beta integral. So this kappa is this kinematic constant. You have 12 elliptic gamma functions in the denominator, numerator, and 2 elliptic gamma functions in the denominator. And here is explicitly the unit circle of. If you impose the constraints that all parameters modulus less than 1, and here is that balancing condition, which in the case of, this is elliptistic condition. The product of the parameters entering the kernel must be some constant. Here it is in these notations. You have quadratic transformation and these things. So you compute, and this integral is computable explicitly. That's a theorem. And the result is triangular product of elliptic gamma functions with t parameters multiplied in this way. So I would like to give you the proof of this function, of this relation, because it's cool, and I would like to show. The problem is very simple. You have to compute some integral, nothing else. No physics, it's analysis, first course of analysis in complex analysis, second year exercise. So the task is for second grade students, compute this integral. How to do it? And you need to be smart, of course. It's not straightforward. Sums of residues do not work, as I said. And here is the method. First, you kill this balancing condition by removing this T6 parameter. You see, T6, by inversion formula, you can write it like this. Then you can write it like this, where A is product of parameters of 1 to 5. So essentially, you remove this constraint. Then you rewrite this relation by dividing left-hand side by the right-hand side. So you form this kernel delta, which is now, you see, the product of this kernel, the ratio of this kernel with this function, written using this particular constant A. And now you rewrite it as the integral of some meromorphic function equals to 1, some normalized. And then here is the smarter step. You have to find the equation for this kernel. It's not differential equation, it's finite difference equation, because you have here, we start from difference equations and you work with difference equations. Here it is. This delta satisfies a partial Q difference equation. So if you scale T1 by Q minus the same function, it is equal to, now you see here you have scaling of X and no scaling, and this G function is written explicitly here. It's a ratio again of theta functions of particular form. Don't try to remember the structure, the particular choice of the parameters. Remember the structure. This is some function G, a ratio of theta functions. Now, how to prove this identity? Very easy. Divide it by delta. And what you will see? Because of the equation for the elliptic gamma function, you will get this identity. Again, some particular identity for theta functions. But you can check that this is actually the elliptic functions identity. All these functions are periodic, p-periodic. You multiply any parameter by p, and it's invariant. This, and this, all three guys. And so it's a ratio, it's an identity for elliptic functions. And how to prove identity for elliptic functions? It's very easy. You take the poles on the left-hand side and compare to the poles on the right-hand side. They coincide. You check, you compute the residues on the left-hand side, and you see that the residues on the right-hand side in the parallelogram of periods coincide. So it means that if you subtract one elliptic function from another elliptic function, you get constant function. because by Liouville theorem, it must be constant. No, it's double periodic and bounded, so it's constant. So you see, this minus this, left-hand side minus right-hand side is constant independent of anything. But then you just pick up particular value of any of these parameters, which kills one of these terms, this one or this one, and you will immediately see that it is verified for constant equal to 0. So again, this proof is one-page proof of the elliptic functions identity. Second smart step. Now we integrate this equation. Integrate over a unit circle. On the left-hand side, you get this difference because the integral is t1 scaled by q in minus integral 1. So, but on the right-hand side, you see how they organized. This x variable, which you integrate over, is scaled. No scaling. It means that you actually, your contour integral, there is some annulus, and one integral is over upper bound, and another integral over lower bound of some analytical functions inside. You impose the constraints that no poles lie inside this annulus, which is written here. If you demand that T1 is less than modulus 1, you see that in this annulus no any pole. So you shrink poles, you shrink the contours of integration, and you get on the right-hand side 0. What did you prove? You proved that your function actually is elliptic. It's the modulus parameter of q. This means nothing than this integral is elliptic. But you have symmetry, PQ symmetry. Therefore, you can just repeat the same story with the P and Q replaced. Now you impose the constraint with P and Q replaced with this one, and you will get immediately this constraint. So it is a triply periodic function. Because in the multiplicative case, it's double periodic, but if you work in additive case, it means that your function has 3 non-trivial periods. But by Jacobi's theorem, it means that it is constant. So what did you prove in this way? You proved that your integral doesn't depend on parameter, T1, which you started from. But because of the symmetry in TK parameters, it means that the integral it doesn't depend on TK at all. It may depend only on P and Q. So you almost solved the problem. Now you have to find the value of this constant IPQ. It's very easy. You take these two particular parameters, a limit when the product goes to 1. What happens is that in your contour of integration, 2 pairs of poles start to pinch the contour of integration. And you just deform the contour in any way you want, pick up the residues, compute the limit, and you immediately see that the constant equal to 1. That's it. The theorem is proved, and why I was so detailed, because this is a cornerstone of this new class of special functions, this relation. It appears everywhere. First of all, this is the elliptic analog of the binomial theorem, Newton's binomial theorem. There is a terminating case, in which case it's called, it goes to so-called Frenkel-Turaev elliptic identity, Frenkel-Turaev sum. But in the non-terminating case, this is exactly this integral identity. It generalizes the well-known Euler's beta integral written here. So that's why it is called elliptic beta integral, because at the bottom you have this relation, these gamma functions. Then it serves as the orthogonality measure for a very rich class of special functions. I will say a little bit more later. It's a germ for infinitely many exact integration formulas for integrals of such type of elliptic hypergeometric integrals. It is not seen, but this relation which I described you, it's related to the exceptional root system E6. I will say about root system more later on. In the lecture by Seok Kim, he mentioned the elliptic Fourier transformation. This relation is a particular example of this Fourier transformation, elliptic Fourier, because you can split your kernel of your integral in 2 pieces, one working as the exponential in the Fourier, so it's a kernel of the integral transformation, and the rest is a test function. So this example that's exactly the example using which I have introduced this elliptic Fourier transformation. And it has very nice applications in quantum field theories, including 5-dimensional cases, which we just mentioned in the morning. So, and this elliptic Fourier transformation actually is defined with the operator which emerges as one of the generators of the Coxeter, well, it's a generator of the permutation groups in the infinite dimensional spaces. So essentially, this you have here the realization of the Coxeter relations, or so-called star triangle relations emerging in the integrable systems. And all this is related to solutions of the Young-Baxter equation, which are quantum integrable systems. This will be described tomorrow in the lecture by Ilmar Gahramanov. So I just remind you that this speaks also inside this relation. And what is most important in relation to today's lecture is the fact that this identity proves the confinement phenomenon in the simplest supersymmetric four-dimensional quantum chromodynamics. So you take four-dimensional n equal 1 supersymmetric field theory with gauge group SU2 and with the flavor group SU6. So one model, electric model, contains this gauge group and flavor group, and the field content is the following. So it has gauge fields, described by adjoint representations of the SU2 group. And you have some chiral superfield in the fundamental representations of the flavor group SU6 and the fundamental representation of SU2. And you compute this superconformal index described today in the morning, which was defined as, where is that? Trace of -1 in the power of fermionic number times exponential of, I will write this. So, -1 in the power of fermions, then P in the power 1 operator, O1, Q in the power O2, and products of these parameters Tk which emerge there, these are flavor parameters in the generators of your flavor group. Then I will write here this curve. This is fermion number. So these P and Q are exactly those PQ which emerge already there. And these are two operators which commute with the supersymmetric charges which you want to preserve. So you preserve one supersymmetry in your many supersymmetric theories. Then pick up all the operators which commute with that supercharges. In this case, in four-dimensional case, there will be two operators plus this what? Okay. Yeah, I can move it, yes. There will be exactly two generators. So basically, this is maximal Cartan subalgebra of your superconformal algebra, preserving one supersymmetry. That's it. You preserve one supersymmetry, ask for maximal Cartan subalgebra. You have two coming from superconformal group, and these are from flavor group. You compute this trace in the quantum field theory, and you will find that it is given by the essentially integral over higher measure of your gauge group times some exponential of, what is called platistic exponential. It emerged already in these lectures as 1 over n. And here you have index in the p power n, q in the power n, and this tk in the power n. So this is called single particle superconformal index. You saw it today in the mornings. So when you compute this integral, this trace, which is given by this integral, you will get precisely the left-hand side of this relation. This is the superconformal index of interacting field theory, supersymmetric. The magnetic dual field theory is free field theory, described by a Vezumino type chiral superfield in the antisymmetric tensor representation of the second rank of the flavor group SU6. And you use, again, the same type of thing without gauge group now, and you will get the superconformal index of that field theory. And this is the right-hand side. And this identity is the equality of superconformal indices in these two simplest, actually, four-dimensional supersymmetric field theories related by electric-magnetic duality, which was suggested by Zyberg in 1994. So, and this is actually the most powerful, the most rigorous mathematical confirmation of that Zyberg duality. That, I guess, is enough to show that, to indicate that this is a fundamental identity which requires, which deserves to be detailed consideration. Just in a flash way, I remind you what is Euler-Gauss hypergeometric function. It's 2f1 series of this type with these coefficients given by Pohammer symbols. Here is the Euler integral representation showing exactly where are the cuts of this function in the complex plane. And here's the definition of the gamma function. What I wanted to stress is that you have the second order differential equation, which you saw already partially in Pierre's talk. This is the hypergeometric equation. So second order differential equation with 3 regular singularities. And the general solution is given as a combination of these 2 functions. And here's the solution, which is analytical near the x equal to 0 points. Well-known story. And this is the Barnes representation, different integral representation of the same function. What I would like to remind you that in the course of quantum mechanics, all physicists were considering exactly solvable cases, or hydrogen matter, whatever. All of them are related to, well, almost all of them are related to this equation, because the properties of this function are very well known, so it's classical special function, and that's going back to Euler and Gauss. And here is this elliptic analog. I jump immediately to that. What you do, you expand. Earlier I had 6 parameters. Now I have 8 parameters in this kernel. So it's 16 elliptic gamma functions, 2 elliptic gamma functions, and you modify the balancing condition. And that's it. This is the elliptic analog of this previous function. If you choose for any, the product of 2 parameters equal to PQ, then they drop out from here, and you get computable cases. This is elliptic beta integral. Now, you the trick. You consider double integral over variables z and w of this particular combination of elliptic gamma functions. So a and b emerge here with separated z and w variables, and here is the mixing variable, and the 4 elliptic gamma functions here. Now it happens because of these constraints that either integral in z or in w can be taken explicitly using this elliptic beta integral evaluation formula. So you do it once in one variable, second time in another variable. What you get? You get this identity. This v function equals to v function with transformed parameters. Here is the law of transformation of these parameters. And up to some multiplication by products of elliptic gamma functions. So it's symmetry transformation obtained in a very trivial way through smart understanding how to do it. What is this? This is a symmetry which, actually, this is the key symmetry expanding the Weil group for A7 root system to Weil group of E7. So essentially, this is symmetry belonging to the E7 root system. And here is just a reminder, what are root systems? So if you take vectors in Euclidean space, here's the basis, scalar product, orthonormal basis. Here's the definition of reflection. Yes?
The order of the Weil group of E7 is huge.
Yes, it's all of them are there. All of them, all the symmetry transformations are symmetries of this function. And I will show one particular one just in the next slide. Yes, all of them are there, just all. And here's the reflection, definition of reflection. You just, you see, add to your original vector x this combination with respect to some particular fixed vector v, and you can check that this square is equal to 1, its reflection. So to see the reflection, you just substitute that your vector is parallel to v, then it's just reflection. If it's orthogonal, then you do not change it, so so that's essentially the meaning of reflection. And the set of such reflections, such that any member of this set is yes, here it is. So as soon as you take any member of this set of vectors and consider the reflections, so all combinations of such type for these reflections, and they do not take you out of this set, it's finite set, then it's a root system essentially. It's called, and the reflections themselves, they are called this is finite subgroup of the rotation group or Coxeter group, and so this is just a reminder what are these root systems. And here is the example of this root system, just to learn. One more point. If this ratio for these particular sets is quantized, it's discrete, integer valued, then it's crystallographic root system, and then this Coxeter group is called Weil group. And well-known for infinite series, 5 exceptional series, 5 exceptional cases. And for instance, for the SUN plus 1 gauge group or AN1 root system, you have these roots of this type. These are orthonormal basis vectors. And the Weil group is just essentially the permutation group. For CN root system, which is symplectic group, then you have these roots. And the Weil group is the product of permutation group times this reflection group. And E8 is the most interesting, perhaps. It will be discussed later, and we've already mentioned when you have the roots of a rather complicated form. This is more or less easy, but this is more complicated. It's a weighted sum of these basis vectors, and the sum of weights here must be even, so it's most complicated. I just remind you, in order to make it more explicit, what I will mean on the next slide. And here is the situation with this v function. So let me denote these tj variables as pq1/4 times the exponential 2 pi xj. Then I have from the balancing condition, I have the constraint that this is actually forming the hyperplane orthogonal to the diagonal in 8-dimensional Euclidean space. And this Weyl group symmetry is evident because I have permutation group in tj parameters is evident. Now, if I take this v function and divide it by this infinite product, here is given explicitly, then that previously given symmetry transformation can be written in this form. You see, it's just invariant, where SIs, where these are the parameters which I already described, but with respect to, if you wish to see it, what does it mean in terms of these xj variables, this you see here, where they are. It means exactly this transformation. So it's reflection with respect to this vector in a dimensional space. 4 in +1, -1 is 8, last 4, the scalar product is 2. And this is exactly the additional generator which you need to add to this permutation group in order to generate the E7 root system with the huge order. And all of them emerge as the symmetries of this function. So this will be invariant with respect to all of these transformations. Because of the appearance of these exceptional root systems, actually, they show that this is a fundamental object. It's an exceptional object. That's why special functions are called essentially special, because they live in special, in this case, special root system. Okay, another exercise. The product of 4 theta functions, short theta functions, for each sign you have to take a separate theta function, plus another 4 theta function, plus another 4 theta function. This equals to 0. This is called addition formula for theta functions. Very easy to prove. I suggest as an exercise with the elliptic functions. A lot of fun, a lot of pleasure when you understand how it works. But this is nothing else than the identity for the kernels of this relation for v function when you multiply particular chosen parameters by q. So if you remove integrals here and divide by kernel, you will get this identity. So this is evident. This is called contiguous relation. And now that's where you embed all this symmetry, these E7 Weyl group symmetry transformations. So from this germ relation, you generate very many identities. And one of them takes the following form. It's again smart. You have to dig out it from there. It has the following form. So you have some elliptic function given here. It's 5 plus 3, 8 theta functions here, 8 theta functions here in the denominator. And U is the particular combination of V function and elliptic gamma function. Here it's written. And this is the identity, which is called the elliptic hypergeometric equation. It's a generalization of that Euler-Gauss hypergeometric equation. It's not very well seen in this notation, but if you can change the notation and rewrite it in the following form. So I introduce new parameters, epsilons, which satisfy balancing condition, and one more constraint. There is a cute one additional constraint. And then these potentials in this equation, you see it's a second order Q difference equation. Q is here and Q inverse is here, so it's second order. And this function is now elliptic function of the 10th order in a sense. So it's explicitly defined functions, and it's solvable. All solutions are essentially given by this V function with different parameterizations of arguments. So general solution of this equation is known, and this is the meaning of the exact solvable equation. And until now, this is the most general equation which can be solved in closed form. And closed form is this elliptic hypergeometric integral, elliptic analog of the Euler-Gauss. Okay, I still have some time. I mentioned this orthogonality measure. What does it mean? It means that there is some inner product, here it is, given as the integral with respect to some measures with some kernel. So you want to have something like this, for instance, for orthogonal polynomials, or wave functions in quantum mechanics for discrete spectrum states. So consider this as just the orthogonality relation for wave functions for discrete spectrum, say in harmonic oscillator. It will lead to Hermite polynomials. You can make it more and more complicated, passing to more and more complicated measure. And here is a very informative table showing you the state of the art at present. Here is the most general Jacobi orthogonal polynomials case. And the measure for that is exactly this Euler's beta integral, which is the normalization of the constant term in these orthogonality relations. Then goes long chain of generalizations over centuries. You see, it's also 19th century. This is, and then goes Chebyshev, Hahn, Raka, and this now increase of these numbers means increase of the complexity of the wave functions, or basically instead of the Hermite polynomials, you have more and more complicated polynomials which are expressed in terms of these generalized 4f3, for instance, hypergeometric functions. At this level, this is the top level called Askey-Wilson level. You stop. It's the most general possible one, for which you can write what is called self-duality relation. But abandoning polynomials in favor of rational functions, you can go further, and here it goes in the next line. And the elliptic case is this one. Here is 1 and 2 here. I will not say about this anything. It's too much information. Just talk about this. So what is this? This is, you see, a complete analog of this guy. You just add here 1, and 1 line here. 3 lines, and you jump from the left corner to the right corner. But this is very complicated elliptic function. It's elliptic function, which generalizes these Jacobi polynomials, Askey-Wilson polynomials, and all other things. And this is, at the moment, the most general function satisfying orthogonality relations. And the measure for this function in the continuous case is exactly that elliptic beta integral. Okay, let's go further. What else? This was univariate case, now multivariate case. A lot of new such type of relations have been found both by physicists and by mathematicians. Why I'm saying physicists? Because after Seiberg suggested his duality in 1994, people started to develop it at tremendous pace, and for 5-6 years until the essential appearance at the CFT, the duality correspondence, they were building models for Seiberg dualities. And as I said, these integral relations, they prove equalities of superconformal indices for Seiberg dual theories. And so physicists, by building Seiberg dualities, actually hiddenly were building such type of relations for elliptic hypergeometric integrals. But of course, that emerged in completely separate context. And here is the example. You have n-dimensional integral over n-dimensional torus of particular combination of elliptic gamma functions. Now you have many parameters, you see. You have this is a mixture of integration variables, and again, this integral is computable. It belongs to the CN root system. And such integrals have, these are meromorphic functions, which you can prove. And it was done by Renz. And if you prove that if you multiply such type of integrals by these infinite products, you have holomorphic functions, which means that all the singularities are known explicitly. That's very good because it gives you analytical structure of this type of integrals. This is type 1 integral for CN root system and corresponds to some particular Seiberg duality for symplectic groups. Here's another type of integral of such type, type 2, which is called. Here you have now a more complicated kernel, which mixes up the integration variables, and in particular you have this T variable. The people knowing Macdonald theory should immediately recognize that this T is nothing else than the parameter which describes the Macdonald orthogonal polynomials business and all the symmetric functions theory hidden behind these things. This is the identity again. You can prove it. And why this is important? Because this is an elliptic analog of the Selberg integral. And Selberg integral is the multidimensional analog of the Euler's beta integral. And it has a tremendous number of applications in random matrix theory, in theory integrable systems, in harmonic analysis on root system, and many other applications. And Selberg introduced himself for number theoretic purposes. And here is the elliptic analog, and again it emerges as the particular relation for elliptic hypergeometric integrals, or as the particular equality of superconformal indices of two field theory, four-dimensional field theories. Okay. I want to give a proof, but let me see what... let me explain first. Where are the root systems in these integrals? You can... Originally, they were interpreted as integrals belonging to root system in the following way. If you look at the kernels of these integrals, you will see that they contain the products of elliptic gamma functions over all roots of that root system. And note that this argument is actually the integration variable. And formally you introduce it in the following way. So integration variable is exponential of this basis vector in your formal Euclidean space. So each integral contains such a piece which shows that your integral really belonging to some root system. But it is natural from the point of view of superconformal indices because these integrals are over higher measures of gauge groups, and when you compute these higher measures, you will see again a similar type of product. So it's two things match. That's how the root systems enter the game. Okay, let me... Yes, I will skip the proof of that elliptic Zellberg integral. You may see on the slides later on the website. The proof is very simple. That's I forgot to mention that the type 1 integral for CN root system is proven straightforward by the straightforward generalization of the method I described for n equal 1 case. So the proof, again, uses finite difference equation, so it's easy. But the second integral which I shown, it's proven in a completely different way, in a purely algebraic way. You just trick way combine integrals and suddenly get the iterative, this recursion relation in the dimensions of the integrals, and starting from known n equal 1 dimension, you immediately compute this Zellberg integral. It's more easy, but more smart. So it's, and tricks are very useful if you wish to learn how to prove the things, not just have physics behind some relations, but also mathematical proofs which actually put the final point on the subject. And here is the final thing I would like to say in the last 5 minutes. It's about the original Seiberg duality. So what Seiberg did in 1995, he took the four-dimensional supersymmetric field theory with SUNC gauge group and flavor group given by the product of three groups, SUNF left, SUNF right. These are arbitrary integers and some U1 group, and some fundamental representation scalar, anti-fundamental with respect to this group, scalar, anti-fundamental. This is gauge group, which is adjoint with respect to gauge, and scalar with respect to flavor. These are baronic charges. These are R-symmetry charges. And using superconformal indices technique, you compute, and you get this. This is the integral on the AN root system now. This is superconformal index for that electric Seiberg field theory. Now you go to the magnetic side of Seiberg's construction. It's more complicated. You have now a gauge group with the rank N tilde C, which is NF minus NC, mixture of flavor and color symmetries. But the flavor group is the same. And field contained is more complicated. You see here you have almost the same as here, two fields, but you have mesonic fields which are gauge invariant and fundamental, anti-fundamental with respect to this flavor group. Rather cute choice of the quantum numbers for these fields, and that's it. He conjectured M. Where you see M? M meson. This M you mean? It's meson. Word meson cut to one letter M. So this is a quark vector field. Quark meson vector field. That's it. That's the meaning of these book letters. So again, you compute this superconformal index for this theory. You get more complicated elliptic hypergeometric integral. Now you have this comes from mesons. This comes from gauge fields. This comes from quarks, and so some constraints. And the theorem states that these two integrals equal. So very special cases I introduced, but the full proof of this relation, much more general than I was considering, was given by Eric Reins. Okay, returning back, what is this all about? This is about the relation of two quantum field theories, showing that these are the same theories in different phases. So one phase, electric theory, works in the, say, ultraviolet regime, and it works in the asymptotically free case, for instance. Another one, say, works in the infrared regime when you have a strong coupling. It's more complicated than right like this, as I said, but that's a general trend for these electric-magnetic dualities. One field theory is in the strong coupling, another field theory is in the weak coupling. But it is the same theory, but it's just in different regimes. So that's the meaning of this duality. And so Zyberg had some arguments saying that this must be like that, and the equality of these superconformal indices, which is a particular elliptic geometric integral identities, prove this duality in the sector of BPS states. So it means that this topological sector of BPS states is the same in these two theories, which is very powerful and comprises all previously introduced Zyberg criteria. Okay. The proofs. Okay, I will skip the proof of how Kreins prove this identity. It's third type of approach to such type of relations. To my mind, too complicated. Simpler proofs must be found. But it's very nice, smart, tricky work with the particular cases of these integrals, showing some theta function identity. So it's the most complicated proof. If you have an interest, you can have a look on that. And on Wednesday evening, I'm planning to come to hotel after 8 p.m., so not tomorrow, but on Wednesday. So if anybody is interested in this thing, I can say more. Okay, and now what is the interplay between physics and mathematics in this case? You see, it's coming in an intertwining manner. Zyberg introduced his duality without, of course, anything of such type of, as I said. Just physics arguments saying that electric-magnetic Maxwell type of duality must exist in the non-abelian gauge theories, and here is the arguments. In the year 2000, I discovered this identity as a mathematician in a sense, although I'm a physicist actually by basic education. And it was proved and published in mathematical literature as a theorem and so on. And so the whole theory of these special functions was launched, and it was developing on its own for 7 or 8, 9 years. And then Dolan and Osborne came up with this interpretation that these integrals can be actually, they describe the superconformal indices introduced by Maldacena, Kini, Minwalla, Raju, one group, and another is Romelsberger from Germany. And so they introduced this notion of superconformal indices, and then in 2008 it was connected to the special function theory, and after that, of course, they started to go together, and here is what has been found useful. For instance, taking physics papers, me and my collaborator Vartanov, we have listed all known cases of dualities and have found about 100 conjectures of this type of relations for integrals, which most of which are still not proven because it's a lot of work. Each proof is very complicated. But it's mathematical part which is missing. But we took what was done by us as mathematicians and interpreted it in the physics side, and it happened tens of new dualities which were missed by physicists. So already the whole picture became much more full than it was before. Still a lot of work ahead, of course. And what I skipped this one. One of the criteria used by Zyberg is the 't Hooft anomaly matching condition for these strong-weak coupling theories. It's the fact that anomalies in two theories must coincide. And it happens that this coincidence is described by SL3Z modular transformational properties of these superconformal indices or these integrals. And they comprise this equality of indices in a quite nice way through the multiple Bernoulli polynomials. I have no time to describe it. So there is a reduction. Well, this was another criteria of Zyberg. I will skip it, how to establish this duality in electric and magnetic theories. What else I can say? So there are, using these integrals, you can see many relations between dualities. So not each duality is separate from another one. You can deduce certain dualities as subcases of another dualities, more general ones. And many dualities can be unified into one master duality. That's what happens through this picture, and it's through the integrals you can easily see it. Then there are Weaver so-called theories, field theories, for which you also can prove this equality from these indices. You can reduce four-dimensional theories to 3 dimensions and 2 dimensions, get equalities of partition functions of those reduced theories, also is inside this story. Then there are cases when these integrals are actually generalized functions. They are defined by Dirac delta functions. So these special cases, and it happens that it's related to the physical phenomenon of chiral symmetry breaking, spontaneous chiral symmetry breaking. Then there are relations to topological field theories by this group of Gadde, Pamonina, Steller, Zamat-Yan, and others also. It's very strongly developed. Then Kim mentioned that all this is related to theories on the curved backgrounds, and he will say more in the last lecture, as he claimed. And these curved backgrounds actually change the topology of space-time and change the topology of these special functions. In particular, if you replace, so basically this, what I described, corresponds to the space-time of the form S3 cross S1, three-dimensional sphere cross S1. But you can replace, for instance, this three-dimensional sphere by length space, so-called more complicated topological space, and repeat the whole story, and you get now these more complicated special functions. These are now sums of integrals, so this is related to superconformal indices of odd-dimensional theories. It will be said more by Kim. And I would like to end by this statement that a lot of work is open, and everybody is welcome to join this stuff. Thank you. Okay.
You mentioned the E7 while group. You also have something that's invariant on the E8 while group?
E8 while group. Partially, yes. So, partially because this elliptic hypergeometric equation is a very special case of elliptic Penlevet equation. Here is the lecturer Yasuhiko Yamada, who will be speaking about elliptic Penlevet equation in a few days. And it is possible to reduce that elliptic Penlevet equation to elliptic hypergeometric equation. And that is exactly a reduction of E8 symmetry, affine E8 symmetry, in his case, to E7. So it's liftable. Answer is positive. More, if there are any. Okay, thank you for attention.